Chapter 17 Interpretation Part 2. In the previous video, we discussed how to interpret the results and performance metrics of a logistic regression analysis. As the second part, in this video, we will see how to interpret some of the metrics in more detail. First, let me explain degrees of freedom for residuals in detail. Degrees of freedom for residuals is the number of observations minus the number of parameters. It represents the amount of information contained in the data that cannot be explained by the model. For example, if there is one predictor variable and the number of observations is 2, the equation of the line representing the relationship between the predictor variable and the dependent variable can be obtained as y equals beta 0 plus beta 1x. In this case, the two parameters are beta 0 and beta 1. Since the relationship between x and y is determined by the straight line defined by these two parameters, there can be no prediction error in the model. However, when the number of observations increases to 3, the third observation may not be on the straight line, and a prediction error may occur. If we increase the number of parameters by 1 and create a plane represented by y equals beta 0 plus beta 1x1 plus beta 2x2, we have a model in which no prediction error can occur. If we increase the number of observations by 1 more to 4, the fourth observations may not be on this plane, and the model will have a room for prediction error. In other words, if the number of observations exceeds the number of parameters in the model may have a prediction error. Therefore, the larger the value of degree of freedom for residuals, which is the number of observations minus the number of parameters, the greater the room for the model to have a prediction error. This is what we mean when we say that degree of freedom for residuals represent the amount of information in the data that may not be explained by the model. Next, let's discuss the concept called degree of freedom of a model. The degree of freedom of the model represents the number of parameters other than the intercept, that is, the number of coefficients included in the model. Here, degree of freedom means the quantified adaptability of the model to the data. How flexibly the model can adapt to the distribution of the data is determined by the slope and shape of the model. For example, a straight line can only adapt to a linear relationship between two variables, while a curve can adapt to a more complex relationship. The greater the number of predictors, the more complex the graph of the model can be, and thus, the greater the adaptive capacity. The intercept represents the predicted value of the dependent variable when all predictors are 0. The intercept adjusts the position of the model, but does not directly affect the slope or shape of the model. Therefore, the intercept is excluded from the calculation of model degrees of freedom, because only the coefficients of the predictors are relevant to the adaptive capacity of the model. The value of pseudo R squared is equivalent to the R squared, or coefficient of determination in linear regression. In logistic regression, the concept of the residual sum of squares cannot be applied directly because the dependent variable is binary. Therefore, the pseudo R squared is used as a concept similar to R squared in the linear regression. Various methods exist for calculating the pseudo R squared. One common method of calculation is McFadden's allure squared, which is calculated by the following equation. Here, the denominator of the fraction is the log likelihood of the null model, and the numerator is the log likelihood of the full model. McFadden's allure squared also takes values in the range of 0 to 1, but it is rarely as high as the allure squared of linear regression and requires careful interpretation. So, why pseudo? The term pseudo is used because this indicator is not a direct analog of allure squared in linear regression and requires a different interpretation. Since linear regression is used to predict a continuous numeric dependent variable, allure squared in linear regression directly describes the rate of variation of the dependent variable. Since the purpose of logistic regression is to predict probabilities, pseudo-allure squared is not a direct analogy of allure squared. Since the pseudo-allure squared is a measure of the goodness of fit of the logistic regression model, it requires a different interpretation than the allure squared in linear regression. Next, let's go on to LL null. The value of LL null represents the log likelihood of the null model. A null model is a model in which the coefficients of the predictor variables are all assumed to be zero. The coefficient of a predictor variable being zero means that the predictor variable has no statistically significant effect on the dependent variable. Thus, a null model in which the coefficients of the predictor variables are all zero is a model that contains no predictor variables with information that predicts a dependent variable, but only information on the intercept. The full model is a model that has been optimized by adding predictors. That is, the model we have constructed for this analysis. By comparing the value of the log likelihood of the null model with the log likelihood of the full model, we can evaluate how much information the predictor variables add to the model. Since the null model contains only intercept information, the comparison between the full model and the null model is to evaluate the extent to which the explanatory power of the model has increased with the addition of predictors to the model. This evaluation can be made by comparing the value of LL null to the log likelihood of the full model above it. The table shows that the full model is a better model than the null model because the log likelihood of the full model has a larger value. However, it is possible that the difference in log likelihood between the full model and the null model is a matter of chance. The LLR p-value is an indicator of whether the difference between the full model and the null model in log likelihood is chance or not. The LLR p-value is the p-value as a result of the log likelihood ratio test, which evaluates the statistical significance of the difference in log likelihood between the null and full models. This value implies the probability that the difference in log likelihood between the null model and the full model is a product of chance. Thus, the smaller this value is, the more likely it is that the superiority of the full model in explaining the data is statistically significant and not by chance. Let me explain the likelihood ratio test. The likelihood ratio test is a test that computes the ratio of the likelihoods of the full and null models and uses that ratio to compare the goodness of fit of the models. The likelihood ratio is calculated by dividing the likelihood of the full model by the likelihood of the null model. In practice, however, the logarithm of this ratio is taken, and multiplied by 2 as the test statistic. The reason for taking the natural logarithm of the likelihood ratio and doubling the difference are based on the following points. First, it improves statistical properties. According to Wilks' theorem, in large samples, the doubling of the logarithm of the likelihood ratio between two nested models follows a chi-square distribution. This makes the statistical properties of the likelihood ratio test mathematically tractable and facilitates interpretation of the results. A nested model is one in which one model contains a complete set of parameters contained in the other model and has additional parameters. The second is scaling. The likelihood itself is computed by the product and tends to be a very small number when the sample size is large. Taking logarithms makes these numbers easier to handle and prevents overflow and underflow. Third, it facilitates interpretation of differences. Taking the logarithm allows the likelihood ratio to take on an additive nature and be interpreted as a difference in goodness of fit between models. This transformation allows for a more intuitive understanding of the degree of model improvement. In this chapter, we have looked at how to interpret the results of a logistic regression model. In model interpretation, it is important to look first at the statistical significance of the coefficients and then to look at the magnitude and direction of the influence of each predictor variable by looking at the sign and absolute value of those coefficients that are significant. It is also important to look not only at the explanatory power of each coefficient individually, but also at the explanatory power of the model as a whole. The log likelihood and pseudo R-squared quantify how well the logistic regression model as a whole explains the observed data. We have also looked at the evaluation measures of the model that are presented as a result of the analysis. In addition to those we have seen in this chapter, there are other performance metrics such as accuracy and F1 score that evaluate the prediction performance of the model. The use of log likelihood and pseudo-determination coefficients and the use of accuracy and F1 score evaluate logistic regression models from different aspects. What the differences are will be explained in later chapters covering accuracy and F1 scores.